Hello, Florence. How's everybody doing? Everybody awake? All right. I'm sick and tired of rehearsing this talk in my head, so let's just get started. All right. So my name is Steen. I'm from Croatia. It's a not uncommon Croatian name. That's how it's pronounced. It's become a running joke amongst my conference friends that they want to try to pronounce my surname. I wouldn't recommend it unless you're from like a Slavic language family, but I guess. So it's Tvrtkovic. So, if you feel like trying it, good luck. All right, so I do some open source in my off time. These are the kind of libraries I work on. I wrote most of these except for attrs, which is in italic, which I am merely the second biggest contributor. Okay, thank you. Some of these you might have heard of. Some of these you may hear of if they kind of pan out in the future. All right, so what are macros? Who here has written C, C++, or Objective-C? All right, so sizable number. So then the contrast is a little off. Can you read this? No. Oh, shit. I have a lot of codes. I have a lot of code snippets. It's going to be interesting. Anyways, it just says defined by something. It's the C preprocessor thing. Turn the lights off. How do I turn the lights off now? Can we turn the lights off? No? Interesting. Well, okay, I think it's just the C. Yeah, let's do that. Ooh, so these are just examples of the C preprocessor. Just pluck them from the Linux kernel. And if anybody has written Rust, you may have seen stuff like this with the exclamation mark. So these are basically kind of, I guess, colloquial examples of macros in programming languages. So a macro would be like kind of a different language on top of your host language that kind of maybe expands or adds some features. Maybe saves you some typing. Maybe allows you to do something kind of more high level in a small number of characters. So Python doesn't have this. So thanks for coming to my talk, I guess. No, I'm just kidding. We do have something else though. We do have a couple of interesting built-ins. We have the compile built-in and the eval built-in. I guess I should stop selecting now. Which are kind of interesting. So the compile built-in basically takes a string, spits out a code object, and eval takes that code object namespace and basically runs it in the namespace. This is kind of interesting. I guess I used to be a Java programmer in a past life. So I don't think it's like a thing in Java. If your Java program is running in production, you can't really expect Java C to be available. I mean, maybe it can be if you kind of set it up, or if you have a Rust program running in production, don't necessarily expect a Rust compiler to be there. But in Python, we do have these. So we're going to get into why they're useful. Now, before we proceed, I would be remiss if I didn't warn you. Eval is kind of dangerous. If any of you remember the log4shell thing, Java fiasco that happened a few months ago with the remote code execution thing. So when you use eval in Python, be extremely careful not to pass in any untrusted data. So any data you might load from the network, from your users, from any place that you might not trust, because you will have a remote code execution thing going on. And it would kind of suck if we had a log4py thing happen in a few months because of my talk. So just be careful, I guess. So let's talk about cattrs first. So cattrs is a companion library to attrs that I wrote in, I think the initial commit was in 2016. It's called cattrs because I wanted to reference attrs in the name, and I'm a cat person, so kind of combine them. So the point of cattrs is it sits in between your attrs classes or any structured data. So it supports a bunch of things nowadays, like data classes and a lot of collections, and it's super customizable, but this is not a cattrs talk. So I'm going to give you the gist. So this is a cattr. This is an attrs class. If you can see the define here, maybe if I can select it again. Sorry about the bad contrast. I guess this is better. So if you have an attrs class or data class, you can import structure from cattrs, and then you just give it a dictionary, and you give it the class, and it turns that dictionary into an instance of the class, coercing types along the way, doing some validation. It works with nested classes, et cetera, et cetera. At the end of 2018, I was kind of finished with the first version of cattrs, like the Gen 1, I guess. I wrote it because I needed it at my job, and I thought attrs was kind of revolutionary at the time because it was one of the first data class definition libraries that was kind of declarative, and that you can kind of ask for its fields, and you can ask it for the types of its fields. Even before we had the type annotation thing, there was a thing where you could pass the type into the attr.ib thing. So even on Python 2, it kind of worked. And this was super interesting to me because you could actually deserialize nested classes, and you need kind of embedded types for this. So when I was kind of done with V1, I still didn't have much uptake so nobody was kind of using the library. And I was kind of sad about it because I thought it was cool, and I wanted the sweet sponsorship bucks. I'm just kidding, because GitHub sponsorships even available in Croatia. But anyway, didn't have much uptake, and so I was kind of thinking about why that is. I was kind of sitting at my computer at night, thinking, what can I do to get people to kind of maybe use this library? So did I go to conferences and talk about it? No, I did not. Did I write like a piece of software that uses it? That would be kind of useful to a lot of people, and maybe kind of promote it like this? No, I did not. Did I blog about it? Did I go to the Zagreb Python meetup to talk about it? I did that later, but at the time, no, I did not. What I did was, I said to myself, well, why aren't people using it? They're probably not using it because it's slow, right? It's like slower than deserialization code you might write by hand. So on one hand, this thinking was quite delusional. On the other hand, it gave us this talk, so just to say if it's good or bad. But anyway, I set out to make cattrs faster. And why was the initial version of cattrs kind of slow? So this is the artisanal structure function. It's what you might write by hand. So if you're trying to create an instance of my class from JSON, you just write a function like this and just use it, right? If you used cattrs v1, cattrs will basically execute a function like the other one, the cattrs structure thing. Now the other one is obviously much slower than the first one, is because it has it basically does more every time you call it. So it basically iterates over the fields of the class, of the attrs class. So there's an iteration going as an iterator allocation. Then for each type, it tries to fish out the handler. That kind of takes time. Then there's some micro optimization. There's this extra dictionary that's kind of unnecessary in this case. So it basically does extra work, so it's just slower. So how do I make it faster? One way is to write it in Python, or I don't know, Rust, whatever. But that kind of sucks. It's not a silver bullet. Then I have to build wheels. I have to. My contributors need to know 2 languages. It's not super good, right? So what occurred to me is, if you're writing this function, how do you write this function? Just look at the class. You look at the types, and you write the function. So all the information you have at your disposal when you write this function manually, I actually have at my disposal when I look at your class. So if you can write this code, well, why can't cattrs write this code for you? So that was kind of the basis of cattrs v2. So nowadays, the way cattrs works is when it sees an attrs class, it basically generates this function right here. So this function is actually, these functions are quite almost identical. Well, the variables are kind of named differently, but dunderCL is, the value of that is my class, and the value of structure my field is integer. So it's actually the same code, right? But so this generated function is not only as fast as something you would write by hand, but over the years we kind of picked up a few tricks. So you see these ugly parameters with default values. This means these values become locals and not globals. Whereas here in your artisanal thing, they would be globals, and locals are faster than globals. So the generated function is actually faster when you write by hand, and I don't think you'd write this by hand. It's kind of ugly, right? It takes a lot of effort. So this is like the first reason why you might want to use cogen is like just pure performance, and cattrs is super fast just because of this. And I think there are other libraries also, so using code generation for performance, I'm not sure, but I think Jinja also uses it, so it's kind of, it's a thing in the Python world at these advanced levels, I think. All right. So after cattrs, let's talk about attrs. So we've already seen kind of an example of an attrs class. So attrs is a library for declaratively writing classes. And what attrs does is basically looks at your class, and it generates some stuff, and it attaches it to your class. So it generates the init, the wrapper, the equals, under equal, maybe the comparison methods if you opt into it, right? And maybe hash. So it generates a bunch of functions. But here's the thing about cogen. If you've ever kind of thought that attrs was like magical and you kind of didn't know what was going on, maybe you weren't aware that you can import getSource from inspect, and you can actually look at the source code of the generated function. And this is, for the my class, this is the exact source code that attrs will generate for you and stick it on your function, which is pretty much exactly what you write yourself. So the magic of attrs is actually in generating these things, but once attrs is kind of done with your class, it's like, this is it. There's no more magic. That's why it's so fast, because it just generates the minimal code that is needed and sticks it on a class, and then it's done. That's why I'm a little skeptical when I see benchmarks saying data classes and attrs are slow, because there's like nothing. I'm always skeptical because there's nothing to be slow here. It's like and you can inspect the source. This is the point. It's like super inspectable. So for example, if you want to see what your equals is doing, what attrs is doing to your equals, you just get source on the equals method. And it just checks if the other class is this class, and then it just compares the fields as a tuple. That's basically it. One other cool thing about this generated source code is that you can actually step through it in a debugger. So here's a different instance of an attrs class. So I just stuck a validator here. So if you run this code under PDB, one of the stack trace levels will be this. This is the source code of the init got a little more complicated because there's a validator involved. But you can look at the source code. It's not complicated. You can see the globals, the locals. You can step through it. It's pretty cool. So that's kind of the second benefit of cogen is, introspectability. Yes. All right. So let's talk about incant. It's like the third kind of case study, if I wanted to be fancy about it. So incant. So cattrs and attrs are kind of battle-tested libraries. You can use them in production. They've been around for a long time. Incant is a new library of mine. It's kind of super experimental. It's me basically playing around with using cogen in a different context of function composition. So I say incant is a library for function composition, but function composition, you can think of it as a dependency injection library because that's like a super common use case for composing functions. So before we kind of go forward, I just want to kind of explain how it works. So there's a little boilerplate at the top. You have to have some state in a dependency injection library, so you just kind of make an instance of incanter. So you have a my function, A, that you want to inject the dependencies into. So you basically register a provider. There are multiple ways to register providers, doesn't matter. So you say incanter.register by type, so this function provides an integer. So if you say incanter invoke my function, since this function is registered, the library will basically use this function to generate an integer and pass it into this function. If this seems a little bit abstract, all right, we just change the names of the types and the functions. So if you have my handler, it's like a Flask handler or something, and it takes a user, you can have a function that provides a user, maybe loads it from the database, loads it from the headers, blah, blah, blah. And then incanter just wires it up. All right. So to demonstrate kind of the third use case for cogen, I'm going to need a little bit of focus from you guys, folks. So we're going to go through a couple of examples. I'm going to ask you questions, and let's see how we can do what I want to get done. So let's say I have a function a. It basically returns none. It takes no arguments. It just prints something. I want to wrap this function. I want to execute some code before this function runs. I want to execute some code after this function runs. How do I do that in Python? Decorator. All right, let's write a decorator. So let's write wrap1, version 1. This is like a super simple decorator. Takes the function, creates a different function, returns that different function. And this different function basically is a closure, so it has this function. So it says print before, calls the function, print after. All good? When I call it, basically what I wanted to happen happens. It's before, inside, after. That's it. All right, cool. I have a different function now. I have function b. This one takes an integer and returns an integer. I wanted to do the same thing, but it doesn't work. I get an error. What do I do? How do I fix this? All right. I make my inner wrapper take args and quarks, and I just pass the args and quarks into the function. All right, cool. I call it. All right, works. Sweet. Making progress. All right. I have a different problem now. So let's say I'm writing a web framework or a dependency injection library or anything like that. I want to be able to inspect the function. Maybe I want to generate open API docs, or I don't know. I want to be able to import signature from inspect. I want to be able to call signature on my wrapped function. But if I do that, I get args, quarks, and none. It sucks. I can't generate open API schemas from this. What do I do? Help me. Wraps? All right. I guess I can import wraps from functools, so I can decorate while I decorate. Anyway, so I apply wraps to my wrapper. All right, cool. I guess that works. If I ask for the signature, I get the signature of the inner function. That's cool. That's cool, I guess. Almost done, though. I have a different problem, though. I want my decorator to actually add an argument. So this x int, I want to use it in my wrapper, but all the other arguments I need to forward to my inner function. So I basically have a signature changing decorator, right? That sucks. Now, how to fix this? There are ways. I've learned yesterday. I think there was a call. There was a talk where the speaker mentioned you can actually get the signature object, you can fiddle with it, replace one or add an argument and stick it back on the wrap function. There are libraries that kind of fix this. There's the wrapped library. It's pretty good. It can produce signature changing decorators. There's a decorator library that also uses CodeGen. Anyway, you know the topic of the talk, so can you guess what I'm going to suggest? So incant is not a decorator library, so it's a little bit awkward to use it for this use case, but it can be used. So I'm going to show you how. Our decorator, we basically rewrite as a context manager. So it basically takes the int it wants, and it basically just has a yield here for the function, and it prints out stuff. So what you say is, incanter prepare. There's the function b, and this is a forced dependency. So the way dependency frameworks kind of work is, your function takes arguments. The arguments are the dependencies of the function. But function b doesn't know about the wrapper, so it's a forced dependency. So we're telling incanter, wrap5 is a dependency of this function, whether this function likes it or not. So just do it. And the syntax is a little awkward because this is a synchronous context manager. That's what this thing means. So what incant will do is we'll generate a function. It will generate exactly this function, which, here's the x. The x goes into the context manager. Here's the I goes into the inner function. And then if you look at the signature works because this is just a function. There's no fiddling. I generated a function with the other signature. That signature has a function. So that's fine. And of course, if you run it, it works because this is kind of the code you would write by hand if you were doing it. But you can do it automatically for any function you want. There's also the added benefit that if these arguments were the same, This function will only have one argument, so you don't have to kind of do the checking. The argument will go to 2 places. So this is kind of the idea of the third use case for CodeGen is you can maybe do things that are difficult to do in pure Python or require fiddling. All right, so in conclusion, CodeGen, super advanced technique. I don't think you're going to be using this in your, I kind of like to think of it as business logic code versus infrastructure code. So if you go to work on Monday, whatever, you have to implement a handler for your product, you're probably not going to use CodeGen because it doesn't really make sense. Cost benefit is not there. Now, if you're going to write a library, you're going to write the next ORM or something, next dependency injection library, you might kind of consider using code generation. All right, that's all I have, I guess. Thank you.
We have a couple of questions.
Right.
How do you test this kind of thing? Not just attrs, but incant or cattrs. What does the test look like?
How do I test it? I test it with a very sophisticated hypothesis test suite. It's difficult to test. You have to kind of check a lot of edge cases. It's not the easiest, but advanced testing techniques in Python like hypothesis really help. And I invite you to take a look at the cattrs test suite. There's a lot of hypotheses in there, and might be interesting if you're kind of a hypothesis user.
Okay. When to use cattrs and attrs compared to native data classes, e.g. Pydantic?
Ooh. Is this you, Hinek?
Yeah, sounds like my question.
Somebody, okay. This is a dangerous question on stream. I can tell you my opinion. My opinion is, so data classes are kind of like the younger brother of attrs. It's kind of a sister library where features from attrs kind of are going slowly into data classes, and we stole some features from data classes that was also good. My opinion is you should use data classes in like maybe 3 scenarios. One scenario is if you're writing code for the standard library, because data classes are in there, attrs is not, so you have to use data classes. If you're writing a script, you might run on a server without a virtual environment, then you can just use data classes because anytime pip is not available, my opinion is you can use data classes. Anytime pip is available, you should use attrs because I don't think there's anything data classes do better than attrs. There are things that attrs that's better than data classes, and the syntax is very similar. And but I am a contributor of attrs, so take this with a grain of salt. And Pydantic has a kind of a different design philosophy, so I won't get into that topic now.
Would it be possible to use this technique, write both a sync and async interface to a single class? I would love to have sync validators in Pydantic, but they need easy sync.
Probably yes. I do have logic for incant. You can inject dependencies into async and sync functions. And the way it works is if it recognizes it's an async function, when it generates the code, it just puts the weight in. So you get the coroutine out instead of a function. So maybe yes.
Any more questions?
All right, well, thank you very much.